We find ourselves living in an age of infinite versions. Somewhere out there, so the story goes, another you is reading these words while sipping coffee instead of tea. Another you became an astronaut. Another you married someone else, moved somewhere else, became someone else entirely. In some distant reality, every road not taken has been travelled, every mistake corrected, every regret undone. This vision of parallel universes has colonized our collective imagination so thoroughly that it feels almost scientific. After all, it borrows scientific vocabulary: quantum, dimension, multiverse, parallel. It appears in films with impressive special effects and novels with technical-sounding explanations. Surely there must be something to it. There isn't. At least, not in the way most people imagine. The question is, what are parallel universes, really? Not in science fiction, where they serve as convenient plot devices for second chances and road-not-taken melodrama, but in physics, where they emerge from the mathematics of reality itself. Consider what happens at a dinner party when someone mentions parallel universes. Everyone nods knowingly. The conversation proceeds as though we all understand what we're discussing. But press anyone, what exactly do you mean? And the answers reveal something interesting. Alternate Earths, portals between realities, meetings with other versions of yourself, different historical outcomes. The Nazis won the war somewhere. You made better choices somewhere else. This consensus understanding feels scientific because it wears scientific clothing, but it emerged from storytelling, not mathematics. It serves emotional needs, not empirical ones, and it bears almost no resemblance to what physics actually predicts. Here is the strange thing. Physicists do take the multiverse seriously. Serious scientists at serious institutions spend serious time contemplating whether other universes exist. Yet what they contemplate shares almost nothing with the popular image. The multiverse that emerges from our best theories is not a consolation machine for human regret. It is not a cosmic warehouse of roads not taken. It is something far stranger, far more radical, and far more philosophically unsettling than any fiction. We cannot help thinking of existence as geography. Evolution equipped us to navigate a three-dimensional world of objects with positions. When we hear parallel universe, we instinctively imagine a place, somewhere we might go if we knew the coordinates, if we built the right machine, if we found the right portal. We think of where as a fundamental question because we evolved asking it. But asking, where are the other universes, may be like asking, what color is jealousy? The question assumes a category that doesn't apply. Picture existence as an infinite shopping mall. Every possible life available in some store, and you happen to wander into this one. What evidence supports this picture? What physics predicts it? What mathematics implies it? The answer is none. The shopping mall is a fantasy. A comforting one, perhaps. The universe, it turns out, does not exist to comfort us. The multiverse, if it exists, does not care about your breakfast decisions. It is not populated by alternate yous living the lives you wish you'd chosen. The popular version serves our emotional needs, the need for consolation, for second chances, for proof that nothing is ever truly lost. These needs are deeply human. They are also completely irrelevant to what the universe actually does. The correction required here is not minor. We are not adjusting details or adding precision to a roughly correct picture. We are demolishing the entire edifice and starting again from the foundations. The real multiverse, if it exists, is so different from the popular conception that even calling it parallel universes imports misleading connotations. So what is the real multiverse? Where did the idea come from, if not from the science fiction that shaped our intuitions? Why do physicists take it seriously whilst rejecting everything the popular imagination associates with it? These questions demand investigation. But first, we must understand something counterintuitive. The multiverse was never the point. It was an accident. No physicist woke up one morning thinking, "Today, I shall invent other universes." The multiverse is not a theory. It is a consequence of theories designed to explain other things entirely. It emerged unwanted and often unwelcome from attempts to solve different problems. The scientists who first glimpsed it in their equations were not delighted. Many were disturbed. To understand this, consider an analogy. Imagine you are building a machine to make coffee. You work out the physics, you engineer the components, you assemble the device. It works beautifully. Excellent coffee, exactly as intended. But then you notice something strange. As a byproduct of the process, the machine also produces a small amount of antimatter. You didn't want antimatter. You weren't trying to make antimatter. You have no use for antimatter. But the physical principles that make your coffee machine work also inevitably make antimatter. The same equations that give you excellent espresso also give you particles of antimatter appearing from the coffee-making process. The multiverse emerged exactly this way. Take cosmic inflation, the theory that the early universe underwent a brief period of exponential expansion. This theory was not invented to produce other universes. It was invented to explain observable facts about our universe. Why the cosmos appears so flat, so uniform, so devoid of certain magnetic monopoles that other theories predicted should exist everywhere. The theory succeeded spectacularly. Inflation explained the observations. It made predictions that were subsequently confirmed. It became a cornerstone of modern cosmology. But its mathematics implied something disturbing. Once inflation starts, it may never completely stop. Different regions of space stop inflating at different times, becoming what we might call pocket universes, separated by still inflating space that expands faster than light. The theory that explained our universe's smoothness accidentally predicted infinite other universes. The coffee machine was making antimatter. Quantum mechanics offers a different door to the same room. The many worlds interpretation was not an attempt to populate reality with alternate versions of ourselves. It was an attempt to take the mathematics of quantum mechanics seriously without adding artificial rules. The standard interpretation requires that the wave function, the mathematical description of a quantum system, collapses when we make a measurement. But this collapse is nowhere in the equations. It was added by hand to match our observations. Hugh Everett, in 1957, asked a simple question. What if we don't add the collapse? What if the mathematics is already complete? The answer was startling. If quantum superposition is real, if particles really can be in multiple states simultaneously, and if there is no moment when possibilities become actualities, then all outcomes happen, not in different places, but in different branches of the wave function that no longer interact with each other. The interpretation that avoids ad hoc additions casually implies a branching tree of realities. Everett did not want this conclusion. He wanted mathematical consistency. The multiverse emerged anyway. String theory arrives at multiplicity by yet another path. To make the mathematics consistent, the theory requires extra dimensions, typically 10 or 11 total. These extra dimensions must be curled up very small, invisible at our scales, but they can be curled in different ways, perhaps 10 to the power of 500 different ways, each yielding different effective physics in four-dimensional spacetime. Each configuration is, in principle, a different possible universe, different particle masses, different forces, different fundamental constants. The landscape of consistent configurations is vast, almost beyond comprehension. 10 to the power of 500 is a number so large that writing it in full would require more digits than there are atoms in the observable universe. The physicists working on string theory did not want a landscape of possibilities. They wanted a unique solution that would explain why physics is the way it is. The landscape was an embarrassment, not a triumph. Yet there it was in the mathematics, as unavoidable as antimatter from a coffee machine. These three routes to the multiverse, inflation, quantum mechanics, string theory, are not the same multiverse. They arise from different physics, predict different structures, and raise different philosophical questions. Quantum branches exist in different terms of a mathematical sum. Inflationary bubbles exist in different regions of an ever-expanding space. String configurations exist in different minima of a mathematical landscape. They share only one thing. None was designed to produce other universes, and none can easily be modified to avoid them. This is why dismissing the multiverse as speculation misunderstands the situation entirely. The multiverse is not a hypothesis someone dreamed up and then went looking for evidence to support. It is a prediction of frameworks that have already passed tests they were not designed to pass. Inflationary cosmology predicted the statistical properties of the cosmic microwave background radiation before we had satellites precise enough to measure them. When we measured them, the predictions matched. The multiverse emerges from the same mathematics. We cannot simply discard the multiverse while keeping what works. The mathematics is connected. The same equations that predict what we can observe also predict what we cannot. This is uncomfortable. It may even be, in some sense, unfair. But the universe is under no obligation to be comfortable or fair. The multiverse gate-crashed the party of physics. It came uninvited through the same door as the guests we wanted, and now we must decide what to make of its presence. If these theories predict other universes, what are those universes actually like? Are they alternate Earths with different histories, as intuition insists, as films depict, as our hearts might hope? Or are they something far stranger? When we speak of parallel universes, we are not speaking of one thing. We are papering over distinctions that matter enormously with a single phrase that clarifies nothing. Imagine three explorers who all claim to have discovered new lands beyond the horizon. The first found branches of a single tree that never touch after splitting, extending in every direction, but separate forever. The second found islands in an ocean that expands faster than any ship can sail, each island receding beyond reach even as you set out toward it. The third found valleys in a mountain range so vast that most contain no air to breathe, no ground to stand on, nothing we would recognize as land at all. All three explorers called their discoveries new lands, but they found entirely different things. So it is with the multiverse. The first explorer, Quantum Many Worlds, found something that isn't really somewhere else at all. In quantum mechanics, a particle can exist in a superposition of states. An electron can be spin up and spin down simultaneously until measured. The standard interpretation says measurement causes the wave function to collapse. The electron chooses one state, and the other possibility vanishes. But vanishes where? How? The equations don't say. We added that by hand. The many worlds interpretation removes the hand-waving. If superposition is real, it remains real. When you measure an electron, you don't force it to choose. Instead, you become entangled with it. You and the electron are now in superposition together. One version of you observed spin up, another version observed spin down. These versions no longer interact. They exist in different branches of the universal wave function, different terms in a mathematical sum. The branches don't split because you made a choice. They split because a quantum measurement occurred. The electron's spin is not what you decided. It's what a particle did when interacting with a measuring device. Most branches differ from ours in ways that are, from a human perspective, completely meaningless. A particle here, a particle there, differences at scales we never perceive, propagating upward into histories that diverge without human significance. There is no direction you could point to indicate where these other branches are. They are not somewhere else in space. They exist in different components of a mathematical object, the wave function, that does not map onto spatial intuition. Asking, where is the other branch, is like asking, where is the square root of 2? The question assumes geography. The answer refuses it. The second explorer, inflationary cosmology, found something that is somewhere else but unreachable. During cosmic inflation, space itself expanded exponentially. Quantum fluctuations during this expansion became the seeds of galaxies. But inflation, in most versions, never fully stops. Different regions of space stop inflating at different times, becoming pocket universes embedded in still inflating space. These bubbles are genuinely separated in space. You could, in principle, point in a direction and say, that way lies another universe. But here is the catch. The space between bubbles is expanding, and it is expanding faster than light can cross it. Nothing violates relativity. Nothing is moving faster than light. But space itself is stretching. The distance between our bubble and any other grows faster than any signal could traverse it. These other universes are not merely far away, they are unreachable, forever, in principle, even with infinite time and unlimited technology. The third explorer, the string theory landscape, found something that isn't a place at all. String theory requires extra dimensions. These dimensions can be curled up in different configurations, each yielding different effective physics. Different configurations mean different particles, different forces, different constants of nature. The landscape is the space of all possible configurations, a mathematical space, not a physical one. Most configurations in this landscape produce physics utterly unlike our own. No stable atoms, no chemistry, no structure, nothing we would recognize as a world. The vast majority of the 10 to the power of 500 possibilities are what we might call gibberish physics, mathematical descriptions of nothing that could support complexity, let alone life, let alone choices about breakfast. Each configuration is a different possible universe, but not a different place. Asking, where are the other configurations, makes no more sense than asking, where is the number 7? The landscape is a space of possibilities, not a space of locations. 3 kinds of other universes, 3 completely different structures, 3 sets of implications that cannot be conflated without confusion. And here is the crucial commonality. None of them predicts alternate Earths. Quantum branches split at particle interactions, not human decisions. Most branches differ from ours in ways no human would notice. Inflationary bubbles likely have entirely different physics, not different histories of the same physics. The string landscape is mostly inhospitable to any structure at all, let alone duplicate Earths with slight variations. The multiverse is not a multiplication of human stories. It is a mathematical structure in which human stories are an infinitesimal thread, possibly unique, certainly not the point. When you hear parallel universe, ask, which multiverse? The answer matters, and none of the answers will give you back the roads not taken. The word unreachable means something different in cosmology than it does in everyday life. If I say a mountain is unreachable, I might mean it's very far away, very difficult to climb, beyond my personal capabilities. But I acknowledge, implicitly, that someone else might reach it, with better equipment, more time, greater skill. The mountain is unreachable for me, for now. The obstacle is practical, not fundamental. Cosmological unreachability is different. The other universes that physics predicts, if they exist, are not unreachable the way a distant mountain is unreachable. They are unreachable the way the past is unreachable. They are unreachable the way north of the North Pole is unreachable. The obstacle is not practical but conceptual. The geometry of reality excludes them from our light cone, permanently and in principle. Consider the inflationary bubbles. They exist, let us say, somewhere in space, other regions where inflation stopped at different times, forming pocket universes separated from ours by still inflating space. You might imagine, with sufficiently advanced technology, launching a probe toward one of these bubbles. How hard could it be? Here is the problem. Space between bubbles is not static. It expands, and it expands exponentially, faster than light can cross it. This does not mean anything is moving faster than light. Nothing violates Einstein's speed limit. But space itself can stretch without limit. Imagine two ants on a balloon. They begin close together and start crawling toward each other. But someone is inflating the balloon. If the balloon inflates slowly, the ants can meet. If the balloon inflates faster than the ants can crawl, they cannot. The rubber between them stretches faster than they can close the gap. Now imagine the balloon inflates faster than light. The ants are not merely having difficulty meeting, they are fundamentally disconnected. No signal from one ant could ever reach the other. Their light cones, the regions of space-time they can affect or be affected by, never overlap. This is causal disconnection. It is not a problem of technology. It is not a limitation we might overcome with better engines or clever tricks. It is built into the geometry of space-time itself. The light cone closes. It does not reopen. Hawking once hosted a party for time travelers. He prepared food, poured champagne, set out decorations. Then he sat alone and waited. No one came. Only afterward did he send out invitations, reasoning that if time travel were possible, the guests would receive the invitations in their future and arrive at the party in his past. His inbox remained empty. Extend this thought experiment to the multiverse. If alternate versions of you existed in other branches or bubbles, and if they could somehow signal across the divide, your inbox would overflow. Messages from infinite yous, each with news from their divergent timelines. Wish you were here. Love, the you who became an astronaut. Your inbox is empty, not because the technology doesn't exist, because the geometry forbids any message from being sent. Quantum many worlds presents an even stranger form of disconnection. The branches do not exist in different places that might theoretically be bridged. They exist in different terms of a mathematical sum. They are not separated by space, but by orthogonality. They literally do not overlap. In the mathematical sense, asking how to travel between quantum branches is like asking how to rotate yourself into an imaginary dimension. The question uses spatial language for something that is not spatial. There is no between the branches. There is no distance to cross. The separation is definitional, not physical. This is what makes the multiverse philosophically troubling. If we could visit other universes, they would simply be very distant places. Interesting, perhaps valuable, but not fundamentally different from distant galaxies. What makes the multiverse strange is precisely that we cannot, ever, in principle. We already accept invisible things into our understanding of reality. We believe in atoms we have never seen, in quarks we infer from collision debris, in black holes we detect only by their effects. We believe in regions of our own universe beyond the cosmic horizon, places so far away that light from them has not yet reached us in the 13.8 billion years since the Big Bang. Why should belief in causally disconnected regions be different? The answer may be that it isn't different, just one more step along a path we have already travelled. Or the answer may be that there is a line and the multiverse crosses it, that permanently unobservable things belong to metaphysics, not physics. We shall explore this question. But first, we must understand something else, what these other universes contain, because even if we could somehow reach them, which we cannot, we would not find what we expect. The multiverse is not a warehouse of alternate Earth histories. This misconception persists because it is emotionally compelling. We want there to be other versions of ourselves living better lives. We want the roads not taken to be somewhere, somehow, taken. We want nothing to be truly lost. The universe does not care what we want, and the multiverse, if it exists, is not designed around human narrative. Consider the string theory landscape. 10 to the power of 500 possible configurations. 10 followed by 500 zeros. This number is so large that meaningful analogies fail. If you wrote one digit per atom in the observable universe, you could not write this number. If each possible configuration took one Planck time to enumerate, the shortest meaningful unit of time, you could not count them in the age of the cosmos multiplied by itself. What do these configurations contain? Mostly nothing. Nothing recognizable, nothing stable, nothing structured. In string theory, how extra dimensions are curled up determines what particles exist and what forces operate. A different curling yields not just different constants, not just a slightly heavier electron or a slightly weaker gravity, but different kinds of physics entirely. Many configurations have no stable particles at all. Others have particles, but no forces to bind them into atoms. Others have atoms, but no chemistry, no way for atoms to combine into molecules. Others have chemistry, but no way to form structures. No stars, no planets, no anywhere for anything to happen. Think of it this way. The Library of Babel in Borges's story contains every possible book. Every arrangement of letters, every possible text exists somewhere on its shelves. This sounds wonderful until you realize that almost every book is gibberish. Random letters signifying nothing. The shelf containing meaningful books, let alone good books, let alone the book you wanted, is vanishingly, almost infinitely small compared to the shelves of nonsense. The string landscape is the Library of Babel of physics. Most configurations are gibberish. They describe nothing we would call a universe, nothing we would call a world, nothing we would call anything. The shelf containing configurations that permit atoms, chemistry, stars, planets, life. This shelf is unimaginably small. The shelf containing configurations that produce something like Earth, with something like our physics, with something like human history, if it exists at all. It is a single book in a library larger than comprehension. There may be no alternate you, not because the multiverse is small, but because the multiverse is so vast and so mostly barren that Earth-like configurations may be unique. We exist, if the landscape picture is correct, in an extraordinarily special configuration, not chosen, not designed, but filtered by the simple fact that only certain configurations permit observers to exist and wonder about such things. Quantum. Many worlds fares no better for those seeking alternate selves. The branching occurs at quantum measurements, events involving particles, not intentions. An electron interacts with a measuring device. The wave function branches. One branch records spin up, another records spin down. The divergence is at the level of quantum events, not human choices. Yes, quantum effects can propagate upward. A quantum random number generator could, in principle, determine whether you turn left or right, creating branches where you made different choices. But this is not the typical case. Most branchings occur at scales we never perceive, in ways that never propagate to macroscopic differences that any human would care about. There is no universe where you chose differently at breakfast. There are universes where quantum events unfolded differently at scales you never notice, creating histories that diverge from yours in ways you could not specify, let alone care about. The many worlds interpretation is a theory about the fundamental structure of reality. It is not a theory about human choices or human narratives. That we have drafted it into stories about roads not taken says more about our storytelling needs than about the physics. And then there is Hawking's final contribution to this question. In a paper published posthumously in 2018, Hawking and Thomas Hertog argued that the multiverse, while real, is not infinite in the way many supposed. Eternal inflation, they argued, does not produce unbounded variety. The mathematics, properly analysed, suggests limited diversity, a vast but finite collection of universe types, not an infinite collection where everything possible happens somewhere. This matters profoundly. An infinite multiverse with infinite variety implies that every possible history occurs somewhere. Every version of you exists. Every choice is made. This is the picture that fuels our multiverse fantasies. A finite multiverse does not have this property. Vast is not the same as infinite. If the multiverse is large but limited, if its variety is constrained, then somewhere you made different choices may simply be false. Even accepting the multiverse, even granting that other universes exist, you cannot conclude that alternate yous exist within them. The consolation fantasy dissolves when examined carefully. The multiverse, properly understood, is not about you. It is not about human stories or human choices or human regrets. It is about the mathematical structure of reality at the deepest level. It is about what kinds of physics are possible and what kinds are actual. It is about why the universe permits complexity at all and whether that permission is unique or common. These are profound questions. They deserve serious attention. But they are not the questions most people are asking when they imagine parallel universes. If the multiverse is real, and if it is forever beyond our reach, and if it contains mostly nothing we would recognize, then what remains? A question. What does it mean for something to exist if it can never be observed, never contacted, never influenced? What does real even mean for something permanently beyond any possible experience? This is where physics meets philosophy, and the conversation, as we shall see, is far from settled. We have arrived at a question that physics alone cannot answer. If something can never be observed, not merely has not yet been observed, but cannot be observed ever, in principle, is it real? What does real even mean for something permanently beyond any possible experience? This is not a new question. Philosophy has wrestled with it for centuries, but the multiverse gives it new urgency and new specificity. We are not asking about angels or abstract numbers or other traditional puzzles about existence. We are asking about predictions that emerge from our most successful physical theories, predictions that those theories seem to require, but that we can never verify. Science, as traditionally understood, requires testability. A claim that cannot be tested is not science. It is something else. Philosophy, perhaps, or metaphysics, or speculation. The multiverse seems to fall on the wrong side of this line. If other universes are causally disconnected from ours, if no signal can pass between us, no experiment can detect them, no observation can confirm or deny their existence, then in what sense is the multiverse a scientific claim? But here is the complication. The theories that predict the multiverse are testable. They are not speculation, floating free of evidence. They are mathematical frameworks that make predictions about our observable universe, predictions that have been confirmed. Inflationary cosmology predicted the statistical properties of the cosmic microwave background radiation before we had instruments precise enough to measure them. It predicted the pattern of tiny temperature fluctuations left over from the Big Bang, fluctuations that seeded the formation of galaxies. When satellites measured these fluctuations, the predictions matched. Inflation passed a test it was not designed to pass. The same mathematical framework that passed this test also predicts other universes. Should we accept one prediction while rejecting another? Can we? The theories are not modular. The mathematics is connected. You cannot simply reach into the equations, extract the multiverse, and leave everything else intact. The same principles that explain what we can observe also imply what we cannot. Consider a detective investigating a crime. No one witnessed the crime itself, but the detective finds fingerprints, traces motives, constructs timelines, interviews witnesses who saw the suspect before and after. Evidence converges on a conclusion that no one directly observed. We call this inference. We call it valid. Courts convict on such evidence regularly. Science works similarly. We infer the unobserved from patterns in the observed. We believe in atoms because of how matter behaves, not because we see atoms directly. We believe in quarks because of collision debris, in black holes because of their gravitational effects, in the Big Bang because of its afterglow. Almost nothing we believe about fundamental physics comes from direct observation. It comes from inference. The multiverse is inference taken to its limit. The evidence, if we call it that, is not direct observation of other universes. It is the success of theories that seem to require them. The detective has no witnesses, no fingerprints, no timeline. But the detective has a theory that explains everything observed, and that theory implies the existence of something unobserved. Is this good enough? Where does inference end and faith begin? We already believe in things we cannot see. We believe in regions of our own universe beyond the cosmic horizon, places so far away that light from them has not had time to reach us in the 13.8 billion years since the Big Bang. We believe those regions exist. We believe physics operates there, the same as here. We believe in their reality, despite being causally disconnected from them, in the sense that we cannot currently observe them or send signals to them. The difference, one might argue, is that cosmic horizons are temporary. Light from those distant regions may someday reach us. Causal connection is delayed, not permanently severed. But is this distinction fundamental, or is it a matter of degree? Consider, We believe the laws of physics operated before there were any observers. The universe existed for billions of years before life arose. No one was there to check. We infer the past from its effects on the present. We believe the Big Bang happened because we see its consequences, not because anyone witnessed it. If inference can reach into the unobserved past, why not into unobserved parallel presents? Perhaps the multiverse simply extends a trust we have already granted. We trust physics beyond our observations all the time. The multiverse asks whether we are willing to trust it beyond all possible observations. There is a philosophical framework that may help here. Model-dependent realism holds that there is no picture-independent or theory-independent concept of reality. We do not have access to reality itself. We have access only to models that connect mathematics to observations. A theory is a model. If the model successfully explains observations and makes accurate predictions, then the entities it posits are real in the only sense that matters. On this view, the question, is the multiverse really real, is malformed. The meaningful question is the multiverse part of our best model of reality? If the answer is yes, if our most successful theories require it, then the multiverse is real in the only sense of real that science can address. Arguments about deeper metaphysical reality are perhaps arguments about nothing, or at least arguments that science cannot settle. This may feel unsatisfying. We want a clear answer. Does the multiverse exist or not? But perhaps the demand for clarity exceeds what reality can provide. Perhaps some questions have no clean answers, not because we haven't found them yet, but because the questions themselves assume more than reality delivers. The multiverse reveals science as more subtle than a machine for producing certainties. It shows us that knowledge has edges, that inference has limits, that the boundary between physics and philosophy is blurrier than we might wish. This is not a failure of science. It is honesty about what science can and cannot do. But honesty creates its own challenges. If we cannot simply declare the multiverse real or unreal, how should we think about it? How do physicists actually navigate this strange territory where successful theories predict unobservable structures? The intellectually honest position is uncomfortable. If you ask a physicist whether the multiverse is real, you will likely get a complicated answer, not because physicists are evasive, but because the question is genuinely difficult. The multiverse is neither established fact nor mere speculation. It occupies strange territory in between. Some physicists believe in it, provisionally. They accept that our best theories predict it, and they are unwilling to abandon successful theories simply because their predictions are inconvenient. If inflation explains the cosmic microwave background, and inflation predicts other universes, then perhaps other universes exist. The reasoning is not certain, but it is not unreasonable. Other physicists suspend judgment. They acknowledge the theoretical arguments, but resist drawing conclusions about existence from mathematics alone. Physics, they argue, is ultimately about observation. Until we can observe other universes, which may be never, claims about their existence are beyond the scope of physics. Still, other physicists reject the multiverse entirely. They view it as a sign that something has gone wrong, that our theories, however successful, have led us astray into unfalsifiable territory. Science, they insist, must maintain its connection to observation. The multiverse severs that connection. Who is right? Perhaps they all are, in different ways. Perhaps this is a question that does not yet have a right answer. Perhaps it is a question that will never have a right answer, in the sense of a scientifically settled conclusion. What does responsible belief look like at the edge of knowledge. Consider an analogy. A map that accurately predicts where roads lead is useful, regardless of whether you've personally driven every road. You trust the map because it has been right where you've checked. You reasonably extend that trust to roads you haven't checked. The more often the map proves accurate, the more you trust it, even for roads far from anywhere you've been. Model-dependent realism treats theories the same way. If a theory accurately predicts observations, you trust it, even for predictions you cannot check. The multiverse is territory on a map whose accessible regions have proven reliable. But there is a limit to this reasoning. If someone claims the map shows a road to Narnia, you would be right to be skeptical. The trust earned by accurate predictions does not extend infinitely. At some point, you need additional reasons to believe. Where is that point? This is the question the multiverse forces us to confront. The universe is not obligated to be fully knowable by creatures like us. We evolved to survive on African savannas, not to comprehend the large-scale structure of space-time. Our intuitions were shaped by objects at human scales, moving at human speeds, in human contexts. That these intuitions extend as far as they do, that general relativity and quantum mechanics work at all, is remarkable, not guaranteed. Perhaps there are truths about reality that we can glimpse mathematically but never verify observationally. Perhaps the multiverse is one of them. This would not make it false. It would make it permanently uncertain, a prediction we have reasons to take seriously, but no way to confirm. Intellectual honesty requires admitting this uncertainty. The physicist who says, "I believe in the multiverse," should add, "but I cannot prove it." The physicist who says, "The multiverse is not science," should acknowledge that the theories predicting it have earned considerable trust. Both camps sometimes overstate their case. Enthusiasts treat the multiverse as established when it is not. Skeptics dismiss it as meaningless when the arguments for it are substantial. The truth lies in the uncomfortable middle, genuine uncertainty that may never be resolved. This is not a failure of science. This is science confronting its own limits. Every successful theory eventually runs up against questions it cannot answer. Newtonian mechanics could not explain the orbit of Mercury. Quantum mechanics cannot reconcile with general relativity. Science progresses by identifying these edges and pushing against them. The multiverse may be an edge we cannot push past, or it may be that future developments will resolve the question one way or another. New theoretical insights, unexpected observations, connections we haven't imagined. Science is not finished. The conversation continues. What we can say is this: the multiverse question has revealed something about the nature of scientific knowledge. It has shown us that physics and philosophy intertwine at the boundaries, that evidence and inference can pull in different directions, that our most successful theories can lead to places we cannot follow observationally. This is humbling. It may also be beautiful. We are creatures who can formulate questions that exceed our capacity to answer. We can reason about regions of reality that we can never reach, structures that we can never observe, possibilities that we can never verify. The multiverse may be unknowable, that we can conceive of it at all, that we can trace the mathematics, weigh the arguments, appreciate the stakes. This says something remarkable about the minds doing the conceiving. The question is not settled. Perhaps it never will be, but the asking matters. The wondering matters. The careful, honest engagement with difficulty. This is what science looks like when it reaches the edge of knowing. And now we turn to a question that is perhaps more important. What does any of this mean for us? If we are one thread in a vast structure, if other universes may exist but can never be reached, if the deepest questions remain open, what place then for meaning, for significance, for wonder? There is a fear that lurks beneath conversations about the multiverse. It goes something like this. If other universes exist, if the cosmos is vaster and stranger than we imagined, if we are a tiny thread in an incomprehensible tapestry, doesn't that make us insignificant? Doesn't the multiverse reduce us to nothing? This fear is understandable. It is also mistaken. The popular multiverse, the one we have been dismantling throughout this documentary, offered a kind of false comfort. Alternate yous living better lives. Roads not taken somewhere realized. A cosmic insurance policy against regret. This vision was consoling precisely because it kept human stories at the center. The multiverse existed, in this telling, to house all possible human dramas. We have seen that the real multiverse, if it exists, is nothing like this. It is not organized around human choices. Most of its configurations, if they exist, contain nothing we would recognize. The quantum branches that split and split and split are about particle physics, not personal decisions. The multiverse is not about you. This can feel deflating. If we were hoping the multiverse would validate our sense of significance, we are disappointed. But here is the thing. Significance was never about cosmic centrality. Consider what we know about our place in the universe, even without the multiverse. We are a species that evolved on a small planet orbiting an ordinary star in the outer arm of an unremarkable galaxy among hundreds of billions of galaxies in the observable universe alone. We occupy no special location. We exist at no privileged time. The universe is not arranged with us at its center. It is not arranged with anything at its center. If cosmic position determined significance, we lost that argument long before the multiverse entered the picture. Copernicus removed us from the center of the solar system. Darwin removed us from the center of life. Modern cosmology removed us from the center of everything. And yet, we are just an advanced breed of monkeys on a minor planet of a very average star. But we can understand the universe. That makes us something very special. The atoms in your body were forged in the hearts of stars that exploded before the sun existed. You are stardust that learned to contemplate stardust. You are matter that somehow became aware of matter. You are configurations of particles that ask questions about particles. This is not diminishment. This is astonishment. The multiverse, properly understood, amplifies this astonishment rather than reducing it. We are creatures capable of comprehending structures that transcend our observable universe. We can reason about causally disconnected regions, trace mathematics that describes places we can never visit, formulate questions about existence that exceed our capacity to answer. We are not significant because the cosmos revolves around us. We are significant because we can comprehend a cosmos that doesn't. The multiverse does not multiply your stories. There is no cosmic warehouse of roads not taken. The consolation fantasy is dissolved, and this, perhaps surprisingly, is liberating. If alternate yous existed somewhere making different choices, your choices here would matter less. Every decision would be merely one among infinite versions, diluted into meaninglessness by the sheer number of alternatives. But if your choices are yours, uniquely yours, occurring in this universe without guarantee of duplication elsewhere, then they matter in a way the fantasy could never match. The multiverse, by refusing to be about you, gives you back to yourself. Wonder is not diminished by understanding. A rainbow understood is not less beautiful than a rainbow mystified. Learning how light refracts through water droplets does not drain the rainbow of colour. It adds depth to our appreciation. We see not only the beauty, but also the physics that produces the beauty, the regularity of nature that permits the beauty to arise. The multiverse, understood, even partially, even uncertainly, is more wondrous than the multiverse imagined. The fantasy version was a projection of human wishes onto the cosmos. The real version, if it exists, is the cosmos being itself, strange, vast, indifferent to our desires, but also capable of producing creatures who can wander about it. Either answer to the multiverse question is profound. If the multiverse is real, we live in a small, observable pocket of something that extends beyond imagination. Temporal, spatial, configurational horizons in every direction, structure upon structure that we can grasp mathematically, but never touch. If the multiverse is not real, if ours is the only universe, then we inhabit something singular and unique, the one cosmos that exists, the only game in town, all the more precious for its solitude. Either way, mystery deepens. Either way, wonder is appropriate. Look at your hand. The atoms there were assembled by stellar nucleosynthesis, scattered by supernova explosions, gathered by gravity into planets, organized by chemistry into cells, coordinated by evolution into organs. You are not merely matter. You are matter with history, matter with story, matter that has travelled billions of years to be here, now, wondering about matter. Now extend this. You are a configuration of matter that can contemplate configurations of physics it can never visit. You can reason about bubble universes you cannot reach, quantum branches you cannot access, string configurations you cannot inhabit. You are, as far as we know, the only kind of thing in this universe that can do this. If that doesn't inspire wonder, consider what would. We began with a misconception. Parallel universes, in the popular imagination, are alternate Earths where you made different choices. Portals connect them. Technology might someday bridge them. Other versions of yourself live out the lives you didn't choose. The multiverse, in this telling, is a cosmic consolation, proof that nothing is ever truly lost, that every road is taken somewhere. This multiverse does not exist. It is fiction wearing a lab coat, fantasy borrowing scientific vocabulary to seem respectable. The physics offers no support for it. The mathematics implies nothing of the kind. What remains is stranger and grander. The multiverse that physics suggests, if it exists, is not a multiplication of human stories. It is a mathematical structure in which human stories are an infinitesimal thread. Quantum branches split at particle interactions, not personal decisions. Inflationary bubbles recede beyond causal contact, likely containing physics utterly unlike our own. The string landscape is mostly sterile, configurations that permit no atoms, no chemistry, no structure. These are not places you could visit. They are not somewhere else in any meaningful sense. They are aspects of a totality that we may be forced to believe in, but can never confirm, contact, or explore. The light cone closes. The geometry forbids. Forever. And yet, here is the wonder we can ask. We can formulate these questions. We can trace the mathematics. We can weigh arguments, consider evidence, appreciate stakes. We can reason about structures that transcend our observations, contemplate entities we can never verify, hold in our minds a cosmos that exceeds our grasp. This capacity is extraordinary. This capacity is rare. In the vast stretches of even our own universe, so far as we know, nothing else does this. Stars do not wander about stars. Galaxies do not contemplate galaxies. Quarks do not theorize about quarks. We do. Creatures assembled from atoms on a small planet, orbiting an ordinary star in one galaxy among hundreds of billions. We have asked whether other universes exist, and we have found that the question is deeper than we knew, the answer more uncertain, the implications more profound than any science fiction imagined. The appropriate response to all of this, to the multiverse, to the cosmos, to existence itself, is wonder. Not the wonder of ignorance, which evaporates when understanding arrives, but the wonder that deepens with knowledge. The more we learn, the more astonishing reality becomes. Every answer reveals further questions. Every understanding opens new mysteries. This is not frustration. This is participation in something larger than any single life. Science is often caricatured as the enemy of wonder, as if explaining things drains them of beauty, as if understanding mechanics kills the magic. The opposite is true. A rainbow is more wonderful when you know the physics. A star is more astonishing when you understand the nuclear furnace at its heart. The universe is more magnificent when you glimpse, even partially, its structure. The multiverse continues this pattern. It may be that other universes exist, that our cosmos is a bubble among bubbles, a branch among branches, a configuration among configurations. It may be that we will never know for certain. It may be that this question belongs partly to philosophy, partly to physics, partly to territories we haven't named. Whatever the answer, we are privileged to live when such questions can be asked. For almost all of human history, the question of other universes was not a question at all. It was speculation without constraint, imagination without discipline. Only in the last century have we developed theories successful enough to make the multiverse a serious proposal, mathematics rigorous enough to trace its implications, observations precise enough to test related predictions. We sit at a remarkable moment, able to see further than those who came before us, unable to see as far as those who will follow. We hold pieces of a puzzle that may never be complete. We contribute to a conversation that began long before us and will continue long after. The multiverse may be real. It may not be. Either way, reality exceeds imagination. Either way, the deepest questions remain deliciously open. Either way, wonder is warranted. 3 principles apply, regardless of how many universes exist. Look up at the stars, not down at your feet. Never give up work. It gives meaning, and life is empty without it. If you are lucky enough to find love, remember it is there, and don't throw it away. These rules hold whether the cosmos is one or many. They hold whether reality is comprehensible or exceeds our grasp. They hold because significance comes from how we live, not where we sit in the cosmic structure. Tonight, if skies are clear, look up. You are seeing light that left stars before you were born, photons that cross the cosmic void, ancient light ending its journey in your eye. Behind those visible stars lie billions more. Behind those, galaxies. Behind those, perhaps horizons we cannot cross. Other bubbles, other branches, other configurations. You cannot see them. You may never confirm them. But you can know they might exist. That knowledge, impossible for almost all of cosmic history, is yours. You are holding in your mind a structure that your ancestors could not have imagined, and your descendants will still be exploring. You are part of a species that asked questions the universe never required it to ask, and occasionally, remarkably, finds answers. The question is not whether another you exists making different choices. The question is what kind of reality would produce the physics we observe. The answer may be vaster, stranger, and more permanently mysterious than we supposed. We began thinking parallel universes were places we might visit. We end knowing they are, if anything, aspects of existence sealed from us forever, present, perhaps, in the mathematics of reality, but absent from our light cones, our telescopes, our possible experience. The universe has grown larger. Our certainty about it has grown smaller. This is not a loss. This is physics doing what physics does, showing us that reality exceeds imagination, that the cosmos is not obligated to be what we expected, that the deepest questions remain open for those willing to ask them. What we cannot reach, we can still wonder about. The wondering is not consolation for what we lack. It is participation in something larger than ourselves, a conversation between mind and cosmos that began with the first upward glance and will continue as long as curiosity survives. The multiverse question remains open. The invitation remains standing. The stars remain above. Look up.